Hi, everybody. So the next thing we're going to do is talk about what are called scores. And a score is an artificial feature that you make by taking a linear combination of existing features. And the idea behind doing this is that sometimes by combining features, by taking kind of a weighted sum of features, you can construct a measure of your data which is more informative than the individual scores by themselves would have been. So just to restate the definition, a score or a linear score is an artificially created feature that is made up of a linear combination of existing features. So if you have a data matrix X, then and you choose weights A1 up to, so there are K features, N samples, K features as usual, and you choose weights A1 up to AK to corresponding to the features, and you define your score for the jth sample to be the weighted sum of the features for the jth sample, where the weights are given by the A1 up to AK. That's an example of a score. If you think about that in terms of matrix multiplication, remember that X0, that's our data matrix where we assume that the columns have mean 0, although that isn't necessary for this particular calculation. When you take your data matrix and you multiply it times the weights, AK, the entry, this is an n by k matrix times k by 1, so it yields an n by 1 matrix. And that n by 1 matrix, its entries, S1 down to Sn, are gotten by taking a linear combination of the columns of X. So it's X1, X0 times its first column, plus A0, A2 times the second column of X, and so forth. So the scores for each of the n samples are a weighted combination of the feature values for that sample. And maybe to make this completely concrete, let's think about an example that everybody is very familiar with. Let's suppose that we have n students in a class, and the data that we have are the results on several assignments. We have the totals on 2 midterms and a final. And those are our features. So our data matrix is n by 3, midterm 1, midterm 2, midterm, and final. And we have for each student the corresponding student's score on those different assignments. Now, your score in the class, according to the syllabus for the sake of argument, is, let's suppose that the midterms count 30% each, and the final counts 40%. Then the weights that we're interested in are 0.3, 0.3, and 0.4. And if we multiply our data matrix, X times 0.3, 0.3, 0.4, we get a vector with n entries where we have here the score for the first student down to the score for the nth student. So the class score in this case is a weighted sum of the features, which are the scores on the individual assignments. Now, you can do this more generally. If we were looking at car data, we could say we want to take a score which is, let's say, half the engine displacement plus the weight of the car. It's not necessarily clear what that means up front, but as we'll see, there's situations in which by choosing these weighted combinations of features, we can extract information that can be buried in the features individually. And of course, when we take a person's final grade in the class, that's what we're hoping to do, is we're hoping to summarize their performance in a single number. Now, one thing, so let's ask, if you have a score, then you can talk about the mean and variance of a score. So the first thing to look at is the mean of a score. And here we're interested in the situation where, let's just remember that our data matrix X0 has columns with mean 0. And our score, which is an n by 1 vector, whose entries are the score for each individual sample, is X0 times A1 down to AK, which are the weights of the features in the score. And the thing to notice here is that a little lemma or a little proposition is that the mean of S is again 0. In other words, the sum as I goes from 1 to n, Si is still 0. So a linear combination of vectors whose sum is 0 is again has sum 0. And just to see why that's true, S is A1 times the first column of X plus A2 times the second column of X, all the way out to A sub K times the last column of X. And now, if we sum up the elements of this, we get A1 times the sum of X0 I1 plus A2 times the sum of X0 I2 plus A sub K times the sum X0 sub IK. Because what we end up doing is we end up summing in A1 we get the sum of all the entries in the first column of X0, and then the sum of all the entries in the second column of X0, and so forth. But these sums are all 0. Because these are the column sums since they're the column sums of X0. And so the sum, if you take S and you think of it as a column vector, and you sum those up, it's again 0. So if you take a score, which is a linear combination of features whose sums are 0, then your score also has sum 0. And a more interesting question is to ask about the variance. And so remember that if you have a score, which is S1 down to Sn, and its mean is 0, then its variance is just the sum of the squares of the values Si. And one way to think about that is it's the dot product of the vector S1 down to Sn with itself, the dot product. Or you could think of it, if you like, as the matrix multiplication, S1 out to Sn times S1 down to Sn. Or, and you can think of this as S, so to speak, S transpose S, divided by N. But we also know that the score S can be computed by taking X0A, where A are the weights. The K weights that define the score S. And if we plug this expression for S into this formula, we find that sigma S squared is 1 over n x0a transpose x0a, which is 1 over n a transpose x0 transpose x0a, x0a, where I've used the fact that AB transpose is B transpose A transpose, which is a fact from linear algebra. But of course, this is A transpose D0A. So we see that the variance of a score can be computed from the covariance matrix in terms of the weights. And if you're interested not just in the variance, but if you have two scores, so let's say you have S, which is x0 a1 down to ak, and T, which is x0 b1 down to bk, these are two different scores computed with different weights, then the covariance ST is, we can write this as x0a and this as x0b. The covariance is 1 over n, B transpose x0 transpose x0a, which is 1 over n B transpose D0. Sorry, no 1 over n here. That's in the D0. B transpose A. So what's really amazing about this is that the covariance matrix doesn't just know about the variance and the covariance of the original features, but there's enough information in the covariance matrix to compute the variance and covariance between any pair of linear scores. So with the initial hypothesis that the means of these things are 0, that was part of the what we needed so that we didn't have to subtract off their means. So to summarize then, what we've shown is that if S is a score with weights A1 down to A sub k, and T is a score with weights B1 down to B sub k, and we can call these vectors A and B, then the variance of S is A transpose D0A, and the covariance of A and of S and T is B transpose D0A. And if this bothers you, remember that D0 is symmetric, so you could take the transpose of this and you would get this, which is equal to A transpose D0B. So the order of A and B doesn't matter in this case. So if you want to think about this in a particular way, as we'll see, this is has a nice geometric interpretation that the covariance matrix tells you how any two scores are related to one another, at least up to what you can measure from the covariance, and also how much they vary. And we'll give a nice geometric interpretation in the next talk.